In this video, I'm going to talk a bit about norms. And the only reason why I want to introduce norms is because it's how we measure error. So, there are a couple of norms to consider. The classic is the absolute value norm, which we all know. And that's generally the one we look at for error in numerical methods. Of course, this has a couple of properties that x plus y is less than the absolute value of that is less than the absolute value of x plus the absolute value of y, which is known as the triangle inequality. Also, we have this nice property that a times x is less than or equal to a x, or actually equal to. There's going to be a lot of times where we're going to be using the triangle inequality to give a very conservative estimate of the solution, saying this could be the worst case scenario and so forth. The other norms are the L2 norm, which is the distance norm. So which is x squared square root, which is initially the same as x. But as you make it longer vectors and add things to it, it becomes more interesting. So in the vector form, and let's just black, and this hopefully will look bold. So the bold form of it, you have some vector x. The L2 norm would be the square root of x1 squared plus x2 squared all the way to xn if it's some vector. So you can see the distance norm, the Euclidean norm as it goes. You can also see it written like that. Then the extension of that is the LP norm, which is given some vector x, p is equal to the square root of the p root of x1p plus x2p all the way up. But once again, this is probably less used. The most common three are the L1 norm, which is the absolute value, the L2 norm, which is our distance norm that we know that is also a vector product, the square root of a vector product. So the L2 norm can also be written as the square root of x dot x. And then there's the max norm. And once again, it's a choice. We have a summation and so forth, but the maximum norm, and once again, which is also known as the infinity norm, is the max of the elements, absolute value to xn. And for different scenarios, you might use different norms. Our default, as I say, is the L1 norm, but actually in machine learning, the L2 norm, or a summed version of the L2 norm, is a mean version of the L2 norm is commonly used. And this leads us into something called Banach spaces, which I'll talk a bit about when we get to the machine learning component. But really, just a Banach space is, and this is definition, a Banach space is a complete normed space. Now, of course, in pure mathematics, there's examples where this isn't going to be. And of course, the norm can change. So L2 norm is more commonly used in machine learning, while the L1 norm is the more common ones that we use for the classical numerical methods. There's norm space. And it observes certain properties that we'll come to. But it's just the terminology, and to hear the word Banach space. There's nothing very exciting about it. It is just a term that says the data I have has to observe some kind of norm. And therefore, thinking about something like the Lipschitz condition, it means that we have an upper bound. So